What specific problem does the PaSa method aim to solve, and how does it improve upon traditional academic search systems like Google Scholar?
The PaSa method aims to solve the problem of conducting comprehensive and accurate academic paper searches, particularly for complex, fine-grained queries that traditional systems like Google Scholar struggle to address. Unlike conventional search tools that often yield insufficient results for specialized queries, PaSa employs a dual-agent system consisting of a crawler and a selector. The crawler autonomously collects relevant papers and navigates citation networks, while the selector evaluates these papers against the user's query requirements. PaSa significantly improves upon traditional systems by utilizing a reinforcement learning framework, Agile, to optimize its search process, resulting in substantial performance gains, such as a 34.05% improvement in Recall at 2.0 compared to Google with GPT-4o. Additionally, PaSa's ability to read entire papers and provide rationale for its selections enhances both the precision of results and user trust, addressing the limitations of existing academic search tools.
How does the proposed PaSa algorithm work? Please provide a detailed, step-by-step explanation of both the crawler and selector's roles in the system.
The proposed PaSa algorithm operates through two main components, the crawler and the selector. 1. Crawler. The crawler begins by receiving a user query and generating multiple search queries to retrieve relevant academic papers. It utilizes a token-level Markov decision process, MDP, where actions correspond to tokens in the LLM's vocabulary. The crawler performs actions such as search to retrieve papers, expand to explore citations within a paper, and stop to conclude its search. It iteratively processes papers in a queue, adding newly found papers to this list, thereby maximizing recall of relevant literature. The training of the crawler involves two stages: imitation learning followed by reinforcement learning, RL, where it learns to navigate citation networks and optimize its search strategy. 2. Selector. The selector takes a Scholar query and a research paper as inputs, generating a decision token, true or false, to indicate whether the paper meets the query's requirements, along with a rationale that supports this decision. This rationale not only enhances the accuracy of the decision, but also builds user trust by providing reasoning. The selector is trained through supervised fine-tuning, and its performance is crucial as it acts as an auxiliary reward model during the crawler's RL training, ensuring that the crawler's actions are aligned with the goal of retrieving relevant papers. Together, these components enable PaSa to autonomously conduct comprehensive academic searches, effectively mimicking human behavior in literature surveys.
Can you give a simple example illustrating how the crawler generates a search query and processes papers based on user input? Please walk through the actions taken by the crawler in this example.
In the crawler's operation, it begins by receiving a user query, such as non-stationary reinforcement learning using UCB-based algorithms. The first action it takes is to generate a search query based on this input, which it then uses to retrieve relevant papers from online sources. For instance, if the generated token is search, the crawler invokes a search tool to find papers related to the query, adding them to a paper queue. As it processes each paper in the queue, if it encounters a token like expand, it extracts citations from the current paper, appending any newly relevant papers to the list. Finally, when the crawler determines it has gathered sufficient information, it generates a stop token, signaling the end of its search session and preparing to pass the collected papers to the selector for evaluation.
What are the theoretical and practical benefits of using PaSa compared to the baseline models? Specifically, discuss improvements in recall and precision metrics observed in the experiments.
The theoretical benefits of using PaSa over baseline models include its ability to autonomously navigate citation networks and read entire papers, which enhances the comprehensiveness and accuracy of academic searches. Practically, PaSa 7b significantly outperforms baseline models in recall and precision metrics. For instance, in the AutoScholar query test set, PaSa 7b achieves a 34.05% improvement in Recall at 2.0 and a 39.36% improvement in Recall at 5.0 compared to Google with GPT-4o, the strongest baseline. Additionally, it surpasses PaSa GPT-4o by 12% in recall while maintaining similar precision levels. In real-world scenarios assessed through Real Scholar Query, PaSa 7b shows A37, 78% improvement in recall at 2.0 and A39, 90% improvement in recall at 5.0 over Google with GPT-4o, further demonstrating its effectiveness in enhancing academic paper search outcomes.
How was the effectiveness of PaSa validated? Describe the experimental setup, datasets used for evaluation, and the metrics employed to measure its performance.
The effectiveness of PaSa was validated through experiments using two primary datasets, Autoscholar Query and Real Scholar Query. Autoscholar Query consists of 33,511 query paper pairs, while Real Scholar Query includes 50 real-world academic queries with manually annotated relevant papers. The evaluation compared PaSa 7b against several baselines, including Google Scholar, and GPT-4o, using metrics such as recall at 2.0, recall at 5.0, and recall at 100 to assess the recall of the top search results. Additionally, the performance of the selector was evaluated using a dataset of 200 query paper pairs, achieving an F1 score of 85% and a precision of 95%. The results demonstrated that PaSa 7b significantly outperformed all baselines, achieving improvements in recall metrics, particularly in real-world scenarios, confirming its effectiveness in academic paper search tasks.
What limitations or drawbacks does the PaSa method present, particularly in the context of its training process or real-world applicability?
The PaSa method presents several limitations, particularly in its training process and real-world applicability. Firstly, the training relies heavily on synthetic data from the Autoscholar Query dataset, which, while high quality, does not fully capture the complexities of real-world academic searches, potentially limiting its generalizability. Additionally, the crawler's training faces challenges due to the long trajectories involved, as it may process hundreds of papers, making it computationally intensive and time-consuming to sample complete trajectories for reinforcement learning. Furthermore, the reliance on a session-level PPO training method introduces complexities in managing sparse rewards, which can hinder effective learning. Lastly, while the selector achieves high precision and F1 scores, its performance is contingent on the quality of the training data, and any biases or limitations in this data could adversely affect its decision-making capabilities in real-world scenarios.